by fixing VG. This is the circuit we are going to use, and this one is grounded. One side is connected to the voltage source and the other side is grounded. Okay, and this is the circuit. Now let's look at some characteristics. First, if you look at the ID current, current is the current that flow through the drain, and in the Mosfet you know that we have a drain and a gate and a source. Since this is an NMOS, the drain is going to be on top, and then gate right here, and then source on the bottom. Okay, and how do you find NMOS or PMOS? You look at the arrow. If the arrow pointing outward, you know that this is an NMOS. And let's look at the ID current and the equation. The ID current is given by K times Vg minus V threshold whole square, and here K is nothing but K is just a constant, and K is given by half Kn W over L. Okay, but you see the equation different in different books. Sometimes they say half K Vg minus V threshold. This one should be VGS. Half K VGS minus V threshold square, and they consider K as K and W over L. And sometimes you see half K and prime W over L VGS minus V threshold square, and Kn is basically mu and COX. So like that, there are various arrangements for this equation. Okay, so that actually, yeah, the Kn is actually mu and COX, this Kn value. Okay, sometimes you see Kn as, they say half Kn, there's no prime, and the Kn is basically the Kn is equal to Kn prime W over L. Yeah, so various arrangement. So if you just remember this, that's the thing. And usually if you have question, the Kn value will be provided in the question, so that's nothing to worry about. And the W over L ratio also will be provided. There will be question like you have to find the width or length, something like that. So various things you can do with this equation. Okay, and let's look at the ID current. This ID current is if you apply KCL over here, whatever the current entering this loop should be the current exiting the loop, and the current exit, the possibilities are we only have gate and source, so it should be addition of Ig plus Is, but the thing is Ig is 0, gate current is 0, it means ID is equal to Is, but this is considering the ideal situation, but in reality the there's a gate current, but that's very small compared to the source current, so that's why we can neglect it. Ig is equal to 0, so it means ID is equal to Is. Okay, now let's see how we can simplify the circuit in order to solve this problem. I mean, if you want to solve this circuit, the best way to simplify this circuit is using the Thevenin's theorem. When we have a voltage divider, if you see voltage divider like this, we can combine and make it into just one voltage and one resistor by using the Thevenin's theorem. Now if I just take the input part of it, input part is whatever inside right here, and here we have R1 resistant, R2 resistant, and we have a voltage source, and this is the voltage in between is the gate voltage, and that one connected to the ground in the bottom. So here if I do that, this is going to be R1 right here, and this is R2, and here we have a gate, and this is the voltage source. Voltage source is VDD, and the first resistance is R1, and the second resistance is R2, and the voltage in between is the gate voltage, and this one connected to the ground. And in the Thevenin circuit, what we do is, in the Thevenin, when we find the VThevenin, we combine this Vg and the ground into one voltage, and we combine into one voltage and put it as one voltage. So in order to do that, we have to see what's the voltage on this R2. So to find that one out, we use the this equation R2 over voltage divider equation, R2 over R1 plus R2 times the voltage source, that's VDD. So combination of all of these is going to be the V Thevenin, and R Thevenin is, if you look at this resistor, these two are in parallel, so R1 parallel to R2 is the R Thevenin in this case. And parallel resistance are, you can find the equivalent resistance of parallel resistor by doing the product of sum. So this is R1 times R2 over R1 plus R2, that's the R Thevenin. And now what we can do is, instead of this whole thing, we can combine them into, put it as just one resistance RG, that's the gate resistance, and we can put it as one voltage, that's VG, that is the gate voltage. Now whatever the rest of the circuit comes out of this. So we just simplified this inside of this circuit by just adding, just putting it as just one resistor and one voltage by doing the Thevenin's theorem application. Okay, after we done the simplification, the circuit is going to look like this. So now we are going to have an RG over here and VG over here, and that is connected to the Mosfet. And here we have VDD, and this is RD resistance, and whatever the current through this is ID current. And then we have source right here, the resistance, the source is RS, and then this one connected to the ground, and the voltage between gate and the source is called VGS, and the voltage between drain and the source is called VDS. And that is basically it. Okay, and ID should be the same current flowing through this, because there's no IG current, because current through the gate is 0, so the same current should be flowing here as well. Okay, so if I apply KVL in the input side, input side is nothing but you have to just consider this as a loop and apply the KVL. KVL is VG minus, and whatever the current through this is gate current, so let's say IG, so IG times RG, and then minus VGS minus ID times RS should be equal to 0, and we know that gate current is 0, so this term will be gone, so we will end up getting VG minus VGS minus ID times RS is equal to 0. So from this one we can say that VGS is equal to let me double check. And also this ID times RS we can combine and make it as VS as well, because that's the source voltage. So VG minus VGS minus VS is equal to 0, and if I write the equation in terms of VGS, then VGS becomes VG minus VS. Okay, this is one of the equation, and if we apply KVL in the output side of the loop, and if you look at the output side, we are starting from VDD, and there's a voltage drop ID times RD, and then here we have VDS, this plus minus VDS, and then this is ID times RS should be equal to 0. Okay, here we can make it simplified by taking the like terms together. So here if I take VDD minus VDS, and for this one I take the ID common, so this one becomes RD plus RS, that's equal to 0, and from this one we can find the equation for the current and VDS as well. So if we take the equation for the current, that one become VDD minus VDS divided by RD plus RS. 3 நிமிஷம். So this is the current equation, and then VDS is equal to VDD minus ID RD plus RS. Okay, this is the VDS equation, and that is it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.